Hello everyone. Today we will discuss about what is a buffer overflow attack and when does it occurs. A buffer overflow attack occurs when a program writes more data to a buffer than it can hold and leading to memory corruption, crashes or even security exploits. In cryptography, buffer overflow vulnerabilities can compromise encryption keys or allow unauthorized access. This is the diagram represents the memory layout of a program. Here the stack represents that it stores function calls, local variables and return addresses, whereas the heap represents dynamically allocated memory and BSS segment represents uninitialized global variables and static variables, whereas the data segment represents initialized global variables and static variables. And finally, text segment contains executable code. This is the diagram represents the function stack frame layout. Here, each function call creates a stack frame which consists of local variables, the previous frame pointer that stores the caller function stack pointer, as well as the return address where the function should return after execution, and also functional arguments. This figure represents function call stack. As function calls are nested, main function calls foo function which then calls bar function. We can visualize this in terms of the call stack and execution flow. Main function is the first function to execute in the program. It calls foo, so a new stack frame for foo is pushed onto the call stack. Inside foo, another function call happens bar. A new stack frame for bar is pushed onto the stack. Bar runs and finishes execution. The stack frame for bar is popped and controls returns to foo. After bar completes, foo continues execution if there are any remaining statements. Once foo finishes, its stack frame is popped and control returns to main function. After foo completes, main function continues execution. Once main function finishes, the program terminates. Here, each function stack is stored sequentially. The current frame pointer tracks the top of the stack. This diagram represents how buffer overflow attack occurs. As we all know that a buffer overflow occurs when the buffer is given more data than its allocated size, and also the excess data overrides adjacent memory including the return address. Finally, this can lead to control hijacking where an attacker injects malicious code. This is the image depicts a buffer overflow attack where an attacker injects malicious code into the stack memory of a vulnerable program. This attack is primarily applicable to languages like C and C++, which allow direct memory manipulation. Left side image represents stack before buffer copy. The stack contains arguments, return address, previous frame pointer and buffer 99 to buffer 0, which represents a local buffer allocated in the function, typically an array or string. Middle image represents an attacker injects malicious code. The attacker exploits a buffer overflow vulnerability by writing more data than the buffer can hold. The overflow allows the attacker to overwrite important stack values including the previous frame pointer and also the return address, replacing it with the address of the injected malicious code. The right side image represents stack after buffer copy. In this, the stack contains malicious code at the top, overwritten previous values like frame pointer and return address. When the function returns, it jumps to the attacker's code instead of the legitimate return address, executing the malicious payload. This image illustrates the concept of using no operation sled to improve the success rate of a buffer overflow attack. Left side image represents attack without no operation sled. In this, the attacker tries to overwrite the written address to point directly to the start of malicious code. However, if the guessed address is slightly incorrect, the program may crash instead of executing the attack. The success rate is lower because even a small error in the written address can result in failure. Whereas right side image represents attack with no operation sled technique. Instead of trying to directly jump to the malicious code, the attacker fills the memory with no operation instruction. Why to use no operation sled? Because the no operation instruction does nothing and simply moves execution to the next instruction. This increases the chance that even if the guessed written address is not exact, execution will still reach the malicious code. This approach makes the attack more reliable because the written address can land anywhere in the no operation region and still reach the payload. This image illustrates how attackers structure bad file to exploit buffer overflow vulnerabilities effectively. In this, the attacker fills the buffer with no operation instructions. The written address field is overwritten to redirect execution into the no operation sled. The malicious code is placed at the end, ensuring that if execution lands anywhere in the no operation sled, it will slide into the payload. The distance between the start of the buffer and the written address is calculated, ensuring precise placement of the exploit. This image represents spraying the buffer with written addresses. In this, instead of single written address, the attacker sprays multiple written values across the buffer. Each written value points somewhere into the no operation sled, increases the chance of hitting the payload. The attacker distributes written values and no operation sleds to maximize the reliability of execution. This method is used in return to no operation sled attacks. This figure explains how to select a valid written address to successfully redirect execution to the malicious code during a buffer overflow attack. In this, the buffer is divided into two sections, one RT section and no operation section. RT section contains multiple written addresses. No operation section acts as a safe landing zone before the malicious code. Then the buffer starts at address X and then valid RT selection range. RT values can be picked from a calculated range. The buffer starts at X. The RT section spans S bytes from X to X plus S. The no operation section spans L bytes from X plus X S to X plus S plus L. Any RT value within this range ensures the program execution jumps to the no operation slide, eventually reaching the malicious code. And then we have to calculate the address. Here we can see address calculation. In this, different values of X are considered to ensure the attack remains effective even if the memory layout slightly varies. Return value must be within X plus S to X plus S plus L to guarantee redirection to the attacker's payload. This figure illustrates what happens to the stack pointer before and after executing the return instruction in a buffer overflow attack, and also it shows how the manipulated return address redirects execution to the malicious payload after function return. This figure illustrates how shellcode is executed after a successful buffer overflow attack. The attacker injects malicious code to spawn a shell, giving them control over the system. In this, figure A represents setting the EBX register. The EBX register is set to point to the bin string on the stack. This prepares the arguments for executing a shell, as well as figure B represents setting EAX, ECX and also EDX registers. Once these registers are set, executing the system call spawns a shell granting the attacker control over the system. This image represents the idea of stack guard. Stack guard is a security mechanism to prevent buffer overflow attacks by detecting return address overrides. Let us see the stack layout. In this, low address represents the vulnerable buffer where user input is stored, and guard represents a special random value placed before the return address and the return address to which execution jumps after the function returns. Let's see how stack guard works. When the function executes, stack guard checks if the canary value, that means guard, is intact before returning. If a buffer overflow occurs, the canary will be overwritten and stack guard will detect the change. If the canary is modified, the program terminates execution, preventing an attacker from hijacking control flow. Stack guard mitigates attacks by detecting return address corruption before execution jumps to an attacker's payload.